This module is about Lewis electron dot structures. Dot structures are very useful in showing the distribution of electrons in molecules and polyatomic ions. This distribution is important because this can determine molecular structure and the reactivity of the molecule. Therefore, the objective of this module is to introduce a systematic approach to drawing Lewis electron dot structures. Let's begin by defining a few terms. The valence electrons brought by each constituent atom in the molecule or ion are distributed as bond pairs or lone pairs. Bond pairs are shared between pairs of atoms. In contrast, lone pairs are localized on individual atoms. While not directly involved in bonding, lone pairs can nonetheless play a key role in determining molecular structure and reactivity. Here, briefly, are the steps we will use in drawing a Lewis electron dot structure. First, decide on the central atom, then count up the number of valence electrons in the molecule or polyatomic ion. Next, we use pairs of electrons as bond pairs to form electron pair bonds between pairs of atoms. Next, if electron pairs still remain, we place them as lone pairs on outside or non-central atoms until each of these atoms has achieved an octet of electrons. If a central atom is deficient in electrons and pairs remain to be used, we place a lone pair or pairs on that atom. If no pairs remain, we use lone pairs from a connected atom to form a double or triple bond. Let's use ammonia, NH3, as our example molecule. First, let's decide on the central atom. We know it's never going to be hydrogen. And the other thing we know is that the central atom is usually the atom with the lowest affinity for electrons. Generally, that means the atom of lowest electronegativity. Therefore, nitrogen in this molecule is the central atom. Next, we count valence electrons. Each hydrogen atom brings one valence electron. Nitrogen, in group 5A, brings 5 valence electrons. This means that we have a total of 8 valence electrons in the molecule, or 4 pairs. Next, we'll draw our molecule with nitrogen in the center of the 3 hydrogens, and then form a single bond between that central atom and each of the surrounding atoms. Creating 3 single bonds means that one of our 4 original electron pairs remains, and will make that pair of electrons a lone pair on the nitrogen atom. The result is that each hydrogen atom has a share in 1 pair of electrons. That's the maximum number it can accommodate. The nitrogen atom has a share in 4 pairs of electrons, 3 bond pairs and 1 lone pair. That is, the nitrogen atom has an octet of electrons. The Lewis electron dot structure for ammonia is completed. Now let's do a polyatomic ion. First, because sulfur has a lower electronegativity than oxygen, sulfur is the center atom. Now count valence electrons. Sulfur, in group 6A, brings in 6 electrons. Oxygen is also in group 6A, so 3 oxygens contribute 18 valence electrons. The fact that this is a negative ion means that there are more electrons available than there are protons in the nuclei of the constituent atoms. Here the charge is 2-, so we add 2 valence electrons to the molecule. This means there are a total of 26 electrons, or 13 pairs. Now we use 3 of those 13 pairs to form bonds between sulfur and the surrounding oxygen atoms. Next, we use the remaining pairs of electrons as lone pairs. Start with one of the oxygen atoms and add 3 lone pairs around the atom. Now the O atom has 3 lone pairs and has a share in 1 bond pair, for a total of 4 pairs of electrons. The atom has a share in an octet of electrons. Now move on to the other 2 O atoms and add lone pairs until each has a share in an octet of electrons. At this point, we've used 12 of the 13 electron pairs. 3 of them are bond pairs and 9 of them are lone pairs. 1 pair remains. The sulfur atom is short one pair of electrons. It has now only a share in 3 bond pairs. So we add the remaining pair of electrons as a lone pair on the sulfur. Each atom now has a share in 4 pairs of electrons, and the Lewis electron dot structure is complete. Let's build the Lewis electron dot structure for another simple molecule, formaldehyde, H2CO. The carbon atom is the central atom in our molecule. Hydrogen is never a center atom, and oxygen is quite electronegative. That leaves carbon in the middle. There are 12 valence electrons, or 6 pairs. 2 come from the hydrogens, 4 from the carbon, and 6 from the oxygen. After forming 3 electron pair bonds, 3 electron pairs remain. Let's place those on the outside oxygen atom to complete its octet. We've now used up all 6 of our electron pairs. The problem is that the carbon atom is short a pair of electrons. We solve this problem by allowing one of the lone pairs on the oxygen atom to become a shared pair between O and C. And we have created what is known as a double bond between the carbon and the oxygen. Most importantly, the carbon and oxygen atoms are each surrounded by an octet of electrons. The Lewis electron dot structure is complete. It is important in chemistry to be able to draw Lewis electron dot structures, and you can be successful if you follow the guidelines. First, decide on the central atom, then count valence electrons. Next, create electron pair bonds. Then place lone pairs of electrons on outside atoms until each one has an octet. Finally, complete the octet of the central atom using lone pairs, if any remain, or form a double or triple bond using a terminal atom lone pair as a shared pair if necessary.